Welcome to everybody. As the title said, this webinar will refer to mechanical energy storage solutions. My idea is to give you a an overview of the state of the art, of the possible application, and of the future perspective and challenges for this technology. So, first of all, I would like to introduce the role, more in general, of energy storage in our power grid system. As you probably are well aware, the electricity grid stability requires a perfect balance between the electricity supplied to the grid by the power plants and the demand, so the loads, the electricity consumed and by all the loads connected to the grid. And this balance has to be perfectly kept in order to have the grid properly working. But what does it happen if there is a mismatch between electricity generation and demand? This mismatch will cause a variation of the system frequency, and this will affect all the system connected to the grid, and in particular, all the generators connected to the grid. As a consequence, you can face some big issues for the grid. Just to give you an idea, of the challenges that we are going to face with the carbon neutral society we are targeting. I have brought you here the example of California. California in the United States is one of the most green states. It has more than 30% of intermittent renewable energy sources in the power generation system. And it happens more than one. It happened in the past, but also in these present days. But during the summers, in particular, when the temperature is very high, people turn on air conditioning and other devices around 5 p.m. when they come home from work. This causes a significant increase in the load connected to the grid. So there is an increase in the electricity demand. But on the other side, the great part of the renewable generation in the system is based on solar power, and solar power is drying up. So the consequence is that the energy system in some cases is not able to maintain the balance between energy demand and production. And this has caused in the past several blackouts, so the total collapse of the grid. And this kind of problem will be more frequent in the future, since the share of the intermittent renewable energy sources will definitely increase in the future. Another example of the challenges related to the presence of a significant share of these renewable sources is represented by the great intermittency and fluctuations of these sources. Here you can see 2 different days in the Spanish market. And in one day, there was the winds were able to cover 64% of the demand of the grid, whereas just a week later, the wind was able only to cover 1% of the demand. So there is a clear fluctuation in energy production due to the wind availability and to the sun availability. And in the future, we are going to face days in which there will be no wind and no sun. This problem is so urgent and so relevant that there is a German word that has been defined for characterizing this situation, and it is Dunkelflaute. So we need a grid able and capable of facing the Dunkelflaute condition. So how we can do it? The first option is to have some kind of backup power plants capable of entering into operation, or capable of increasing or decreasing the power production whenever it's needed. In the power system at the time being, there are 3 different types of power plants capable of doing this kind of operation: hydro and pump hydro power plants, nuclear power plants, and more in general, fossil fuel power plants. But it is clear that this third option, the one based on fossil fuels, it will be not available in a carbon neutral society. So this possible solution of the challenge of the grid stability is not fully, is not enough. We need to find another option, another solution. And this second option is represented by energy storage technologies. We need to have in our power system a significant share of energy storage technologies, because only these technologies can support the system in case of extra loads. For example, discharging discharging themselves and providing to the grid the required energy. And in case of extra renewable production, charging during and exploiting this excess in renewable production. Moreover, our grid is changing, and it's important to highlight also this aspect. In the past, we were used to have a top-down supply system with very big generation system based on nuclear and on fossil fuels, and with a distribution from the top to the bottom and to the consumers according to the scheme that is represented on the left of this figure. But it's clear that our grid is evolving to a more complex system, well represented by the figure on the right, in which there will be several levels, and all the levels will interact by exchanging loads and generation. There will be a huge decentralization in the energy production, with small wind and PV power plants distributed in our grid and generating power. But there will be also loads and other systems like companies, industries consuming electricity. So in this complex situation, we will need to include the storage system in order to support the grid in all these levels. So in the future, in our future, in the smart grid of the future, there will be a definite increase in complexity. And in such a context, the energy storage system will definitely play a key role. Of course, depending on the needs, these storage technologies will be required to have different characteristics and to provide different services. Just to give you an overview, depending on the application, we will need to have a power system very fast in reacting, or energy storage system with providing a long-term and a long capacity of storing energy. So different characteristics will be required to all these storage technologies, depending on the discharge time and on the time frame we are looking at. There will be technologies required to react in a very fast way or slowly. We will need power storage system capacity, large or small, depending on the application, with the possibility and capability of ramping up and down the power in a certain time period. And then we will have also the need of large energy storage capacity, capable of storing energy for a day, for week, for month, or even for season, in order to cover, for example, the heating needs of a country for an entire season. To face all these requests, all these needs, there are indeed already several storage technologies available. In this figure, you can find a non-exhaustive list of some of them. And in this webinar, we will focus on the mechanical energy storage. And in particular, within this big family of mechanical energy storage solution, there are several options. I do not have time to enter into the detail of everything, and I have chosen to focus my attention on 4 of them. Pump hydropower, in terms of conventional and both unconventional solution, liquid air energy storage, flywheel energy storage, and gravitational energy storage. So let's start from the first one, pump hydropower. Why I have decided to start from pump hydro? Because pump hydro is definitely one of the most important and the oldest mechanical storage solutions. As you can see in this graph, provided by a report of the International Hydropower Association, at world level, the pump hydropower plants are well spread in several countries, going from the west to the east of the world. And it is already playing a significant role among storage solution and in the grid, in maintaining the grid balance. The principle of the pump hydropower plant is very simple. It's like a green battery. You have like for hydropower, two different reservoirs, an upper one and a lower one, and you have an hydraulic machine or an hydraulic system in the powerhouse capable of operating in two different modes. The classical one, the generating mode, is the one of the hydropower plant. So when you need to produce energy, when you need to release power into the grid, the water is released through the turbines from the upper reservoir to the lower reservoir, and the gravitational energy of the water is converted into kinetic and pressure energy. And the machine in the powerhouse is capable of generating electricity using exploiting this energy. But if you have to store energy, if you have to store energy produced by the grid, the operating mode of this power plant is reversed. The water is pumped back from the lower reservoir to the upper reservoir, and there it is stored until it will be necessary to produce again. So as you can see, in this case, it is called a green battery because the storage mean is water, which is pumped back in case of storage need. Here I have just summarized the average general performance that can be expected from this kind of solution. The typical power at the time being is between 200 up to 350 megawatts per unit. With head ranges, head is the difference in level between the two reservoirs, with head ranges between 100 and 1,500 meters, so a very wide head ranges, and around the trip efficiency, which is quite good. It's between 75 and 85%. The energy capacity is huge. You can reach up to 10 gigawatt hour of energy capacity with discharging time greater than 8 hours. In some cases, the discharging time could cover weeks in case of needs. So it can be seen also as a seasonal storage solution. The technical lifetime is in between 40 and 80 years. And I will show you the factors that are capable to affect even negatively this lifetime. In terms of configuration, there are two main configurations that you can find of pump hydropower, the open loop and the closed loop. The difference between the two is the possibility of having a natural flowing water into the upper reservoir or into the lower reservoir or not. In the open loop, the reservoir, one or both of them, are continuously connected to a natural flow source, like, for example, a river connected to one of the two reservoirs. In the case of the closed loop, the two reservoirs are isolated, so you have two natural or artificial reservoirs managing a certain amount of water in both modes. So, of course, both of these configurations have some issues in order to be managed, because you have to consider the inputs and the outputs of the rivers connected to the reservoir in the first case. But also in the case of the closed loop, you have to properly manage your water amount in order to be sure to be able to provide the storage capacity or the generation capacity in case of needs. Looking more into the detail of the hydraulic machine inside the pump hydropower plant, you can have two different configurations. And it is important to highlight this because this configuration also affects the characteristic of the power plant. One option is to have a ternary set. The ternary set is composed of a pump, which is connected through a clutch to a turbine on the same shaft. And both the machines are connected to one single electrical machine that is able to operate both as motor or as generator in case of needs depending on the needs. On the other side, you have a binary set in which not only the electrical machine is reversible, but also the hydraulic machine is reversible. It is just one hydraulic machine which can operate both as pump or as turbine, depending on the needs of the operation of the plant. Here you can see a detail of the pump turbine, and its way of operation is quite simple because depending on the flow direction and on the rotation direction of the machine, you can use this machine as a pump or as a turbine. If it is a pump, if it is operated in pumping mode, the water flow enters from the right and then it is discharged from the left, from the so-called spiral case of the machine. If you want to operate in turbine mode, the water enters in this direction, the runner rotates in the opposite direction, and the water is discharged from this pipe. So in the binary set is extremely simple, is more economic than the ternary set because you have just one hydraulic machine. But you can imagine that the transient mode, the need of changing between pumping and turbine mode requires a certain time because you have to reverse the water direction and also the rotation direction of the machine. So the main challenge for this set is in the fast reaction, in the rapidity of the transient period. Pump hydropower in its different configuration, both in ternary and in binary configuration, is, as I was saying before, is an old technology. We can find in our power system the first pump hydropower plant even in the 40s of the 19th century, so of the 20th century. So it is definitely one of the oldest storage technologies that we have. There was a peak in the installation of pump hydro during the 70s and the 80s. And the main reason of this first peak was related to the use of pump hydro as support plants for nuclear power plants in case of blackouts, for example, to guarantee the safety of nuclear power plants and also their start back after a blackout. This application requires from pump hydropower plant a certain characteristic, completely different from the characteristics that are required now by the new grid, by the future grid that I have described to you at the beginning of this webinar. Here you can see an example of an old power plant located in Italy. It was built in the 70s and it is already operating. But as I said, it has been designed and it has been operated for certain condition in almost fixed operating points without any request of flexibility and without any request of a rapid reaction to the grid needs. On the other side, the grid complexity is increasing. The grid scenario, the electric grid scenario is completely changing, and pump hydro is required to change its role in this context. So in this graph taken from a report of the US Department of Energy, you can see as the pump hydropower have already seen a renaissance at the beginning of the 2020s, and a second peak in installation has been foreseen between 2024 and 2026 in order to cover the market needs for storage in this period. Of course, since, as I have shown you, the power plants are big with a huge capacity, energy capacity and power capacity, this new installation will cover the needs of the grid for certain years. But a second rise is expected starting from 2030 because of the new needs of the clean posed by the clean energy transition. An example of the new generation of pump hydropower plants is represented by the Nandedrans, but this power plant commissioned in 2022. It's a very new pump hydropower plant. Again, the power availability is huge with 900 megawatts of power. And this can be seen as the new generation of pump hydropower plants already seen in order to face, already designed in order to face the request of the future grids. In particular, this new generation has been designed and thought in order to cover faster reaction time needs required by the grid stability. And as you can see in this graph, the new generation represented by the pink bar of the graph has definitely increased the capability of pump hydropower plant to react to request of the grid with a reaction time of the order of seconds, whereas in the past the reaction time of the oldest pump hydropower plant was in the order of minutes. So this new generation has already included some requests of the future grids. And in particular, the main technologies included and developed for this new request is the so-called variable speed technology. The variable speed technologies included in this new generation of pump hydropower plants provides more than one benefit. In particular, it allows to increase the operating range in turbine mode in order to be able to generate more power even at partial loads. It added regulation capacity in pumping mode for binary configuration, because in the past pump turbine had no regulation capacity in pumping mode. And it also allowed to increase the efficiency in power production and in pumping mode when the power plant is required to regulate the frequency of the grid. This variable speed option has been enabled with significant innovation regarding the electrical machine of the power plants. In particular, the technology of the doubly fed induction machine has been introduced, In this technology, a frequency converter of a power equal to 1/3 of the nominal power of the power plant has been introduced, and this has enabled the possibility of varying the rotation rate of the machine in a speed range between plus minus 25%. But a second option has been also introduced recently, which is the fully fed induction electrical machine. These machines is equipped with a full-size frequency converter, and it has enabled the possibility of varying the speed range in a extremely wide time range interval from plus minus 100%. So the full possibility of completely varying the speed from 0 to 100%. Of course, this comes at a price. Fully fed are much more expensive in comparison with doubly fed, and depending on the needs of the power plants during the design phase, it can be foreseen to use one option or the other one. Another important innovation introduced in pump hydro power plants is the so-called hydraulic short circuit. It has been tested in real power plants in a European project recently ended, the X-Flex Hydro project. And it is a sort of secondary hydraulic circuit created with the goal of enabling the simultaneous operation of pump and turbine in the ternary group. So as I said, in ternary group, you have two different hydraulic machines, one pump and one turbine. In the past, it was possible only to operate them individually, so only in pumping mode and only in turbine mode. But now with this secondary hydraulic circuit created, it is possible to operate the machine, the two machines in a separate way. Of course, this will require to use the so-called quaternary group, so to add an electric machine in order to have the possibility of operating both the machines simultaneously. The advantages of this solution is that it increases the operating range in both modes, since the net power of the power plant is equal to the difference between the power absorbed by the pump and the simultaneous power generated by the turbine. So if the pump is working at 80% of its load, in terms of power absorbed by the grid, the net power will be regulated by acting on the power generation of the turbine. So this significantly increases the operating range of the power plant and the regulation capacity in pumping mode. The last but not the least advantage of this solution is that it significantly reduces the response time for changes in operating mode, because you don't have one single machine, you have two different machines, and the possibility of exploiting this secondary hydraulic circuit makes the transient much faster than in the old configuration of pump hydropower plants. But there are indeed some challenges for hydropower, for pump hydropower. So despite the fact that, as I said, is one of the oldest technology present in the market, these new requirements from the grid poses challenges. Some of them has been faced, some are still under study. In particular, the request of flexibility, which is common for all the storage technologies in the grid, will affect the performance of the reliability of this storage solution. In particular, one aspect will be a significant increase in start and stop for the hydraulic machine and for the power plant. But this again comes at a certain price. It has been estimated in this study that one start and stop cycle shortens the refurbishment time period by 15 hours. So if you imagine that in the best scenario, the plant will be required to have from 100 to 500 start-stop cycles per year. But in the worst scenario, this technology can be required to have 30 start-stop cycles per day. You can imagine what kind of impact this can have on the reliability and on the life of the equipment of pump hydropower plant. Moreover, this flexibility will also require fast power ramp up and down with significant stress on the mechanical components. So the main challenge at the time being for supporting the clean energy transition is to find a new solution for enhancing the flexibility of the existing technology and also for limiting the impact on the plant life and on the stress on the mechanism in order to make this solution sustainable even from an economical point of view. Moreover, we have to consider that the climate change is also impacting the standard operation of pump hydropower plant. There is a clear increase in concentration of sediments in water due to the glaciers melting. And moreover, we have already seen in these last years a significant fluctuation in water availability going from droughts to flood condition. So this will further stress the flexibility in operation of this power plant, and it will be necessary to develop new solutions for the smart and sustainable management of this power plant, and also for reducing abrasion on the mechanical component due to this increased concentration of sediments. So even if it is an old storage solution, new challenges have been posed and new solution will be required. Moreover, there will be also a significant request of increasing the potential, the installation of pump hydropower plant, and this will push to the exploitation of unexploited and unconventional solution. So I would like also to present some of these unconventional solutions, but because these will represent the future of this storage solution. The first one is the so-called seawater pump hydropower plant. In this configuration, the main difference with the standard pump hydropower plant is that the lower reservoir is the sea. So you can imagine, as it has been done in this demo plant in Japan, that you can use the sea or the ocean as a lower reservoir, and you can build an artificial reservoir close to a coast. And this enables the possibility of having a seawater pump hydropower plant with a significant increase in potential installation site. This solution has advantages. There is a greater flexibility in operation because the lower reservoir has an infinite capacity and you can exploit it for increasing the flexibility of your power plant. Moreover, there is a reduction of the civil work cost because you have just to build one reservoir, the upper one, whereas for the lower reservoir, it is necessary only to build a breakwater structure around the discharge zone of the plant. And as I said, there will be a greater increase in the number of potential installation sites because you can exploit all the coast in which there are some hills or some mountains close to the coast. But there are some challenges mainly related to the use of salt water. You need to face significant corrosion problems. And this will require the use of coatings with an increase in the cost, and with also the need of considering an increase in maintenance activities. Moreover, the artificial reservoir, the upper reservoir, will need waterproofing coating in order to avoid the penetration of the salt water in the ground around the reservoir. And last but not the least, the components in the powerhouse have seen the growth of marine biofuel, and this has created further problems and the need of more frequent maintenance. So you can imagine all these challenges are not so easy to be solved. And the reality is that this pilot was, the operation of this pilot has been concluded in 2016 because these challenges have created some problems. But this solution is not dead with this pilot. The technology has been improved. Significant step forward has been carried out in terms of coating, in terms of maintenance activities for limiting marine biofueling, biofouling. And a proof of this is represented by the fact that a utility in Italy has designed and has proposed the construction of a seawater power plant in Sicily. This power plant is now under the authorization process, and it has quite relevant dimension and size, with the pumping power of more than 300 megawatts and the generation power of about 250 megawatts. The cost is not negligible, $500 million, but it's clear that it shall be sustainable from an economical point of view if this company is moving on with this proposal, and if it intends to build it. Another unconventional pump hydro solution is represented by the underground configuration, in which the upper reservoir is located on the ground and the lower reservoir is located underground, as you can see in this figure. Of course, this will again increases the possibility of exploiting more sites, because you reduce the dependence on mountains and on difference in heights to have an installation site. But on the other side, it has been demonstrated in the last year that the civil work cost regarding mainly the underground reservoir are extremely high, and this causes some problems in terms of economic sustainability. Because of this, it has been seen that to make it sustainable, it's important to adopt one of these two options. The first one is to use already existing sites like abandoned mines, so to exploit abandoned reservoir, abandoned caves, in order to minimize the civil works. This opens some challenges from the technical point of view, because you have to study in detail the dynamic of the hydraulic circuit. But it's an option that could make sense from an economical point of view. And on the other side, a second option is to apply circularity principle in the design phase. And in particular, the possible use of the residual material, of the waste material extracted from the ground during, as a consequence of the construction of the underground, the possible use of this waste material in secondary, for secondary purposes. If you are able to sell this material in order to be used in other and in other configuration, in other sites, in other ways, this can make the business model sustainable from an economical point of view. A third and most and more recent option is the so-called high-density pump hydropower plant. In particular, a UK company has proposed a solution in which a patented fluid, the R19, is used as a fluid. So instead of water, this technology uses a fluid having a density 2.5 times the one of the water. And this will enable the possibility of creating a pump hydropower plant with a smaller dimension but similar powers. And you will need smaller heads. So the advantages of this solution are clear. You can reduce the cost of the construction because the scale of the plant is significantly reduced. And you can increase the number of potential installation sites because you will need smaller heads instead of big mountains in order to have a solution which makes sense from a technical point of view. But this solution is rather new. A small demo site of 500 kilowatts is under construction in UK, and the solution will be developed, improved in this demo site. And this, as soon as this demo site will be able to operate, this will enable further investigation on the technology potential and on the reliability and on the performance of this patented fluid R19. This is the demo site under construction. It is expected to be commissioned in March 2025. So it could represent a really interesting option for for increasing the potential of a pump hydropower plant. Handed this first big parenthesis on pump hydropower plant, I would like also to give you a brief overview of the other mechanical energy storage solutions which are available on the market. The first one is the so-called liquid air energy storage. This refers to a technology that uses liquefied air, or in some cases also nitrogen, as a storage medium. And it belongs to the family of the cryogenic energy storage technologies within the main group of mechanical storage. How does it work? The charging phase sees this process when there is an excess of the electrical energy. This electricity is used to clean the air and to feed a compressor in order to compress the air, refrigerate it, and store it in terms of liquefied air. Then this liquefied air is stored in an insulated tank at a temperature that can go from minus 150 up to minus 190 Celsius degrees, and approximately at an ambient pressure. And when it is necessary to generate electricity, in the discharging phase, the air is pumped, is reheated in order to evaporate, and it is expanded in an expander in order to be able to generate electricity and in order to give the electricity back into the grid. There are also secondary circuits exploiting the heat and the cold that are generated by these compression, refrigeration, evaporation, and expansion. And these secondary circuits are extremely useful to increase the round-trip efficiency of this technology. The performance are summarized in this table on the left. As you can see, even in this case, the energy capacity can be quite relevant. The cycle efficiency, the round-trip efficiency is around 60%. And the response time is not so fast. So it is definitely not of the order of seconds. We are in between 2.5 up to 10 minutes, with a technical lifetime of the order of 40, 60 years. The main function, given this general performance, are also summarized in this second table. This technology cannot provide for sure primary frequency regulation services, but they can provide peak load energy supply. They can support the grid in balancing the supply and the generation. And yes, there are already some examples. There was a first pilot plant at the University of Birmingham, but also at the time being, there are companies in the market proposing this solution, like, for example, the MAN company and the Sumitomo company. Still, some challenges remain, because if we want to increase the round trip efficiency, it would be important to improve the secondary circuit, so the possibility of exploiting the waste heat and the waste cold in the process. And this will enable the possibility of increasing the round trip efficiency. And we can also maybe work a little bit more also on the compressor and the expander in order to try to maximize their performance. Another very important mechanical storage solution is represented by flywheel. What is a flywheel? A flywheel is a very simple concept. You have a rotating mass, which it's put in rotation at a very, very high velocity in a vacuum environment. And the rotating mass is connected to an electric machine, which can work both as motor and as operator. So a flywheel is a kinetic energy storage system, again, within the family of mechanical storage system. And the storage principle, the storage concept, is based on the exchange between kinetic and electrical energy through an electrical machine. If you have to store electricity, you convert the electrical energy into kinetic energy, so into rotation energy of the mass. If you have to produce electricity, the cycle is reversed, and the kinetic energy is exploited by the electrical machine to generate electricity. One peculiarity of this technology is that energy and power are decoupled. The energy is mainly related to the rotating mass. So the dimension of the rotating mass are extremely important to define the energy capacity, whereas the power that can be released by or absorbed by the system is related to the electrical machine, because the power depends on the state of charge, we could say, of this technology. In this case, the state of charge is represented by the kinetic, by the rotation velocity of the mass. So depending on the rotation of the mass and depending on the kinetic energy that you can exploit, you are able to release or to absorb a different power. The performance of these technologies are quite different, I would say, from the two previous one. The round trip efficiency is high, is of the same order of pump hydro, 80%. And the energy capacity and the power capacity are relatively small. As you can see, it goes from 100 to 1,500 kilowatts, and the energy capacity is in between 10 to 100 kilowatt hours. So it's a relative small energy capacity and a small power. But the main peculiarity of this technology relies on the discharge time and on the response time. It can discharge in terms of in a time frame of the order of seconds and minutes, and it is capable of reacting to an input in almost an almost instantaneous way. We are talking about milliseconds of time of reaction. So this is an extremely fast way of reacting, and this explains also the general characteristics of these technologies, because it has, as I said, a low storage capacity compared to batteries or other storage option, but it has a very high power density, because the power, as I said, is related to the speed, and the speed ranges is extremely important. It can rotate up to a velocity of 30,000 run per minute, which is quite impressive. Moreover, it does not suffer from the number of cycles, so you can use this technology for an unlimited number of cycles. And the temperature range in which it can operate is quite wide, from -20 up to 70 degrees. And it is extremely sustainable, since it is mainly based on the use of standard materials like steel, for example, and it does not include any polluting or critical raw materials. These explain why this solution is already commercial. There are several companies which have proposed pilot and commercial solution, as you can see in the list on the right. It's interesting to highlight that all these solutions are used for frequency stabilization, because as I said, this is the main application field of this technology. It reacts in a very fast way, and it can provide a very intense power ramp up and down. The application are related, as I said, on high power, low time, and fast response, and are listed here on the left. The most relevant, I would say, is frequency response, but it can be used also for providing UPS services, or for working on the electrical power quality and reliability. But there are still some challenges for future development of these technologies, because to increase and to improve the energy density, it is important to work on the materials and to test the new composite materials with this purpose. Moreover, in order to reduce the mechanical losses related to the speed rotation, superconducting magnetic bearings are under investigation. Moreover, to improve the round-trip efficiency, high-speed permanent magnet motors are also under investigation. All these challenges will enable the possibility of increasing the time of reaction, further increasing the time of reaction, and also of increasing the energy capacity of the technology. Last but not the least, this will also, as I said, increase the capacity of an array of flywheels in order to enable the possibility of using it at a grid level. The last storage solution that I would like to discuss with you is the gravitational storage. This is a quite new solution. But it is based on a very, very simple concept. So the idea in this case is to store the energy, the electrical energy, in the form of gravitational potential energy. And when you have to absorb power, this power is used to drive an electromechanical equipment to lift a mass at a certain height, in order to store the mass energy potential. When it is necessary to release electricity to the grid, The motor generator unit reverse its mode, and the mass is allowed to lower its height in order to convert the gravitational energy into electrical energy. One example of this storage solution is the so-called tower. The tower has been proposed by a company called Energy Vault, and it is based on bricks of equal dimension. Of course, these bricks are made with high density material, and these bricks are placed at a certain height to store the energy, as I said, as a form of gravitational energy. And then there is an equipment with motor generator unit and ropes that moves these bricks in this tower, depending on the power needs and on the needs of absorbing or generating power. If we have to highlight the strengthness and the weakness of this solution, it's clear that this solution is independent from the location. You can build this tower wherever you want. It's also extremely easy to scale, and it has a quite high round trip efficiency, around 80–90%. There are still some weaknesses because the TRL is not so high. The technical maturity has to be further investigated, and at the time being is not sustainable from an economical point of view in small scale scenario. But as I said, it is definitely an interesting solution because there are companies proposing different configuration of this gravitational storage. The first one was Energy Vault, with two different pilot sites built in China, with the power capacity between 17 and 25 megawatts, and an energy capacity of around 100 megawatt hour. And as you can see, it's like a tower and a system that can take the bricks of the tower up and down depending on the needs. Very similar configuration have been proposed by other companies, like in this case by the company called Gravitricity. In particular, in this slide, you can see the Gravistore solution. Even in this case, there is a big mass whose height is controlled by ropes, moving on fixed pulleys and connected to a motor generator unit. The efficiency is of the same order of the previous configuration, around 80%, with a life expectation of 50 years, mainly related to the reliability of the ropes and of the mechanical system. Our first pilot site has been built in Scotland, near Edinburgh, with a power of 250 kilowatts. So it is promising, but even in this case, the economical sustainability has to be investigated, because it would make sense to have the mass underground, but the civil works related to this underground configuration are not negligible in terms of from an economical point of view. The last configuration proposed for the gravitational energy storage solution is the so-called piston. In this case, you have a mass which is like a piston, and this piston is located in a closed loop hydraulic circuit. This configuration is a sort of hybrid with a pump hydropower plant, because the piston height represents the gravitational energy that is stored, and depending on the pressure created by the hydraulic circuit, the piston height can increase if you have to absorb power, or decrease. In particular, the pressure and hence the position of the piston is controlled by a pump turbine pumping the water below the piston. When you have to charge, So when there is a surplus of power, the power is absorbed by the pump turbine, in particular by the pump, and the pump pressurizes the water under the piston, and this lifts up the piston into a higher position. When you have to discharge, so when there is a power shortage, the piston is released downstream. It pushes the water, so it reverses the water direction, and this enables the possibility of generating electricity through the pump turbine operating in this case as a turbine. This configuration at the time being is only on design phase, we could say. There is a company which have proposed already a pilot solution whose costs are estimated around $140, $360 per kilowatt hour of energy capacity. So, as I said, there are no pilots for this configuration, and the storage capacity mainly depends on the power of force of the radius of the piston, whereas the cost depends on the square of the radius. So it's quite clear that to make it sustainable, it would be useful to have a large installation, because the storage capacity will increase, but the cost not so much. Anyway, this is just a design phase, and no pilots are present at the time being. To conclude this webinar, I would like also to give an overview in terms of future perspective of a possible hybrid solution. Because as we have seen, there are a group of mechanical energy storage solutions. Each solution has its own characteristic, its own performance, and can be suitable for operating in different contexts depending on the needs. But it would be interesting also to investigate the possibility of hybridizing one of these mechanical storage solution with other storage solution or among themselves. There are already some hybrid solution under investigation. For example, one of the most investigated at the time being is the hybridization between pump hydropower plant and a battery energy storage system. There are pilots under construction, and some experimental test in real operating condition has been already carried out in a European project. But also multiple configuration can be designed. For example, in our research team, we have investigated the possibility of hybridizing pump hydropower with batteries, but also with another mechanical storage, flywheels, a flywheel energy storage system, because this combination will enable the possibility of exploiting the best characteristic of the different storage technologies in order to optimize the output. And which could be the way of operation of this hybrid system. We have studied a lot this configuration. I will not enter into the detail, since it is out of the scope of this webinar, whose goal was to give you just an overview of the solution. But in an hybrid power plant like the one I was mentioning, a proper control strategies can be put in place in order to react to an event of frequency variation from the grid. So as you can see in this scheme, if the grid is suffering of an under frequency event or of an over frequency event, this event will require the hybrid power plant to provide a certain power ramp signal up and down depending on the needs. And this power ramp can be shared among the different technologies depending on their characteristic, in order to try to optimize the output, but also to preserve the technologies and to maximize their life and their efficiency and their operation capacity. For example, as you can see in this case, in case of an under-frequency event, a proper control strategies can assign to the flywheel, whose graph is reported on the up top right, can assign to the flywheel to respond to the a very high frequency of the grid signal, because as I have already discussed, flywheel have no problems in the undefined in unlimited cycles, so, and are very fast in reacting, so they can easily follow the high frequency content of the grid signal. Whereas BESS can take the battery system, can take care of the medium frequency content, since this will reduce the number of cycles, which has an impact on the battery life, but can also provide some regulation and fast response. Whereas pump hydro power plant, whose characteristics of reaction are slower, but can provide an important power ramp up and down. Pump hydro can take care of the power range of the power ramp, but in a slower with a slower reaction time. So taking care of the slow component of the frequency content. And these can be optimized, reducing, for example, the wear and tear of the pump hydro power plant, but not only. As you can see in this graph, on the z-axis, there are indexes of the wear and tear of the pump hydro power plant, and you can minimize this index with a proper combination of flywheel and batteries. And the optimization changes depending on the goal and on the needs of the hybrid configuration. But the point is that it's feasible, and it can add benefits to the grid and also to the technologies involved in the hybrid configuration and providing storage services. So to conclude this webinar and this presentation, I have given to you a brief overview on the mechanical storage solution. As I said at the beginning of this webinar, it's difficult to enter into the detail of all the mechanical storage technologies. There are other, like compressed air energy storage solution, which have been proposed and deserve to be considered in the mechanical storage scenario. But I decided to focus only on some of them in order to try to give you the overview on the different characteristics of the technology included in the mechanical storage family. Of course, as you have seen also, these technologies have different level of development, different stage of development. There are old solutions like pump hydropower, which are in need of evolving, of renaissance and renovation related to the new request of the grid. And there are very, very new solutions with their own peculiarities, like the gravitational energy storage, which will enable and increase the possible application for mechanical storage in the grid. Is there a best one? Is there a solution which could be the solution, the one supporting the grid and supporting the clean energy transition? At the time being, in my opinion, there is not. I have shown you the graph. There are several needs for the future grid. The grid is increasing in complexity. There are needs in terms of fast storage capacity, in terms of power capacity, in terms of energy storage capacity. with on a long-term scenario, arriving even at a seasonal time period. So we are going from needs of milliseconds of time reaction up to needs of seasonal storage. This entire range cannot be covered by one single technology. So my opinion to conclude this webinar is that a complex and interconnected power system is expecting us in the future, and we cannot expect just one technology to be able to solve all the problems. So mechanical storage technologies can be used. They have to be used depending on their characteristic. They have to be used depending on the specific application. Certain are better for certain application and other are better for other application. But hybrid configuration can really represent an added value. Hybrid, not only within mechanical storage solution, but also with the hybrid in the whole energy storage family, because hybrid solution can merge the characteristic and the performance of the component technologies, and can optimize everything in order to really represent a good option to support the clean energy transition. So my final comment, my final statement in this webinar is that we need to move on with the research. We need to move on to the technology development, always considering a hybrid as a good option to optimize everything. And with this final statement, I really thank you for your attention, and I'm open to question if there are any.